Alright, so we were talking about MCPs. Okay guys, let's start. Okay, is that me? Okay. Alright, so we're talking about MVPs and whether or not we can extend these naturally to the temporary unbound case. So the way to do that, or one way to do that, is introduce this discount factor gamma. And then if we think about the message passing and what's the adaptation to balance equations? Well, it's very simple. The only thing that happened was that we have a gamma as a prefactor for the message passing scheme. Okay, so this new value is given by your current utility plus this, and this is called the Bellman operator. All right, so that's nice. This is our future. This is our current value. Is a new value. Now, the thing though about this is that another thing to say is that before we had messages which were functions of time, right? So in the finite time, we had these utilities, a function of time. We had these messages, mapping from some time point to another time point. But the thing that's a little bit not so clear is in the Bellman infinite time case. First of all, how do you initialize this operation? Right. So how do I say what is the value of x at big T? Well, I don't have a big T. It's infinite. Right. So I can't initialize this thing. Similarly, I have no concept of time in the future. I have no. Everything's an infinite time. There's no fixed time. So what I really want is I want to consider the situation where I'm considering such a long thing that things have converged to some sort of temporally independent values. So what that means is that we don't have any time indices anymore on this Bellman equation. So this means that this v is just a function, the value is just a function of the state that you're in. Right? This is the Markov transition here. I put t is just to denote the two time points, but they are really just this. If we assume homogeneity in the Markov process, right? This transition matrix distribution here doesn't depend on time. And then this value is just a value in the original Bellman equation of the future thing, but here it's just the value of the state. So what this means is that you might think, how can I solve Bellman's equations? How can I do dynamic programming when I have an infinitely long chain? Well, the point is, in some sense, you can't do dynamic programming because there's nowhere to start. But in the infinite limit, Bellman's equations, in the case that things are converged, they converge to this equation. Right? So this is a kind of a little bit of a conceptual thing. So we couldn't do dynamic programming in the infinite case, but we can do it in the finite case. We can write down what the algorithm is for that finite case, and we can infinitely extend into the infinite time extension of the algorithm. Right? You see? It's kind of a weird thing. So if I said, I have an infinitely long Markov chain, you might not know where to start because there's no, I don't even know how to start dynamic programming. So what we do is to start with a finite chain. You write down the dynamic programming algorithm, and then you extend the algorithm to the infinite time case. That's the way to do it. Or the way to do it. And that's what we're doing here. It's kind of a little bit awkward, but then your task is to find, so you know what U is, the utility of being in a particular state, you know what this transition is, and you know what gamma is. You need to find V, which solves this equation. So before, you see, it's different. In the dynamic programming case, there's no question of solving it. It's just like every time we do the update, you know what the new V is, the new value is. Right? You solve it as you go along. Here, I don't know the value. I have to implicitly find it as a solution of this Bellman equation. Right? So I cannot apply. I have to find some way of solving this equation in the infinite time case. this is making much sense. Does it make sense? Does it make sense? It kind of makes sense. I think it makes sense. I guess I would say that. Anyway, let's imagine that you. I'll come on to how to solve this thing in a sec. But let's imagine you solved it. Then the optimum decision, if you're in a particular state, say S, what is the optimum decision you should take? Well, it's that one which gives you the optimum expected value, as before. But there's nothing changed in the general setup. The only thing we now need to do is to figure out what this value is. And there are a couple of well-known ways to solve this. One is called value iteration. So the idea here is we just guess some initial value. So let's think about the finite state case. Right? So what are these things here? Let's say there are 100 positions in the maze. So S goes from 1 to 100. So we need to find the value for each of being in each of those 100 maze positions. So this is a 100-dimensional vector. This quantity here, this transition matrix, given a state D, is just a matrix. It's a 100 by 100 matrix, indexed. We're going to have a collection of such matrices indexed by decision. So we're going to have a V there. This is corresponding length, obviously, to matrix vector multiplication. Now we have to do some operation on that. We have to do a max over the collection of matrices that do. Right? And then that gives us a new vector, which we add to the utility vector. That gives us the thing. So what we could do is in the value iteration, we say, well, I'll guess some thing for the value, this 100-dimensional vector, randomly. I call that V old. And then I'll just update the new V by that Bellman operator. Okay. And then you get a new V, and then you plug that in. You say, well, my new V becomes my old V, and I'll do it again. And I keep going around, iterating this recursion until convergence. Does it converge? Yes. It's guaranteed to converge. As long as gamma is less than 1, it's you can show it's guaranteed to converge to the to the correct value. Okay. So if this gamma is large, close to 1, then the convergence numerically is slow. If it's small, it's fast. That's value iteration. Another way to think about this is pulse iteration. Now, what we do here is we say, well, let's imagine that I know what the optimal decision is. If I am in some particular state, yes, what is the optimum decision to take on that? And in the end, this is really what we care about. So let's say I assume I know that. Right? I know the mapping of a particular state to optimal position. Whether I should go left or right at this particular position in the maze. So I know D star, I guess, that's my assumption. So if we go back to, this is the Bellman equation here. So if I know actually what the optimum thing to do is here, say, so if I'm in the, yeah, so D, so if I know the state S, I know the optimum decision to take already. What that means is that I don't need to do the max over D anymore. It's already given to me. This is just an assumption. If I assume I know, given S, what is the optimum decision to take, then this max is redundant. And what the effect of that is to linearize this recursion. So I've now got V on the left, I've got a linear operation here, and I've got a V on the right. So this is just a set of linear equations which I can solve any way I like, counting elimination. But if I want to, I can just formally write this down. I can say, well, this Vs is like the S component of a vector V. So this Us is like the S component of a vector U. This P is like the S prime S element of a vector of a matrix P. Because I know now what the position is not a function of D anymore. So So that means in matrix notation, this becomes V is equal to U plus gamma P transpose times by V. So we can just solve that. So V is equal to the inverse of this matrix, which is given by U. Now, this matrix is given because we assume we knew what the optimal decision is as a function of the state. Right? But we didn't actually. That was just a guess. So, the procedure in policy iteration is you guess what the optimal policy is, what is the given state S, what is the best decision to take. Assume and make some initial guess. That tells us actually what the optimal decision is, so what the value is. We just solve the value straight away. Right? But if we know the value now, we go back to here, well, given the value, I can tell you what the optimal decision is. Right? So that's the closing of this loop. So now we've got a new d star of S, and we then resolve for the V, and we resolve for d star. We keep going backwards and forwards, and that's policy iteration. So policy iteration has the effect of linearizing Bellman equation as a linear function of the value. And we can solve that using Gaussian elimination. But just another sort of minor point is that what I'm writing down here, it's just algebraic in the sense that obviously this is matrix inversion multiplied by your utility. But in reality, of course, you will not actually use matrix inversion numerically to solve this problem. You'll use Gaussian elimination or something like that. And typically, one should not explicitly compute the inverse of a matrix and then multiply it by a vector unless it's strictly you really want to know what the inverse matrix is. If you just want to, this is just saying solve this linear equation. So you would use Gaussian elimination or some corresponding reason, which is usually more numerically stable. Okay, so let's look at an example. So we're going to run some demos. Okay, so what's happening here? I'll try to explain it by going back first here. So we're going to have we have a set of positions. Okay, so there's a grid. It's like a maze, if you like. It's a 15 by 15 maze. So there are 225 points in this maze. This forms our state space. Okay, so 225 states. Some positions in this maze are more favorable than others, a priori. They have a higher utility. And what they will be is that all states have got zero utility except for, in this case, I think 3 states will have utility 1. Okay? I'm allowed to move from this maze to a neighboring square in this maze in 1 time step. And then I will start, say, maybe the question is, what is the value then of any of these particular states? So I know the utility that's given is 0 except for 3 specified positions. The question is, what is the value of each of these positions, these states? And that's what I need to calculate using either value iteration, policy iteration, or some other procedure. And what I'm plotting here, this is the final converged value, okay, of each of the states. And what would you do? Well, you would then take the decision. Let's say that you are now at this particular location here. You need to take the decision which gives you the highest value, right? And your accessible states to you are your neighboring states. So you would either go to this one or to this one because they are the highest value states. Okay, so then you say you go to there, and then you do the same procedure. You say, which state neighboring me has the highest value, and your decision is to go to that. Expected value of the transition. So we're assuming here that these transitions are, if I say I want to go to the square to my right, I can go there with probability 1. So how does that look? So that's what I'm trying to I'm going to show you now value iteration first, then we'll do policy iteration under a random. So there are 4 positions here. The utility was blue for 1, red for 1, and blue 0. And this is value iteration filling out, looking above, from the top now down to, in this case, a 10 by 10 grid. And you see it converges to some final. This is policy iteration then. This is something else. Okay, so if you, there are some characteristic things you can see there that the policy iteration tends to converge more quickly than the value iteration. But the update operation is more expensive, so to solve the set of linear equations each time. But the number of iterations required is smaller. Okay, so yeah, so just to re-emphasize again, so we started out, this is the value, the converged value surface. We started out with the utility surface, which just had a spike at a small number of positions. Wherever these are, will correspond to the highest value position in this case. Then wherever you are, you will take that decision to move you to the neighboring square with the optimum value. That's the optimum thing to do to get the maximum expected utility in operating in this environment. So it seems kind of clear. Let's look at another example. So in this case, so here the idea is that you're an airplane pilot, and you basically have an environment. So what's going to happen is that these points in red are good. In the sense you're allowed to go there. You have a high utility or low cost. These points in blue are disasters. Okay, as you're flying the plane. So you're looking down, and this red bit here corresponds to the runway. Okay, so you can land here, and then you can taxi around to your terminal. But you don't want to land off the runway, otherwise you're in trouble. Similarly, there are some wealthy villages around this airport. But if you fly over them, you're in big trouble. Okay. So the question is, if you're in this environment now, some particular location, what trajectory do you take to get you to the, what's the best way of getting down here, flying down to get to here? So you're going to get utility, which is good if you go down here, and I can't remember exactly what the utilities, the numerical values are, but I just want to show you what the kind of situation looks like. So this is value iteration, I think, going along. So filling in these, updating these utilities with their actual values. So that's it, that's the converged value surface. So if we were, for example, then, let's imagine that you're here and this state at this time, right? So the question is, how do you, from that place as an airplane pilot, how do you fly ultimately to the runway? For, you know, it's not the shortest path, because the shortest path will go through this village with lots of neighbours, so they're going to complain a lot. That's bad. Costs the airline a lot of money. So you want to avoid the villages. So you know, we go to this neighbouring state with the highest value, and it's this one. We keep going to this neighbouring state with the highest value, etc. It goes down here, down here, down here, and we end up with a big prize of getting to the parking the plane correctly. Yeah.
But would it not be more optimal to go on the surrounded block on the left?
This one here, but that's a little bit further, isn't it?
Well, not because when you go down, you still have to go left, so it'd be shorter to go to the left and go down. And then turn left one block higher than.
Yeah, I think maybe I forgot the exact setup actually of this problem. I think that there's a small probability that if the airline pilot says he wants to go, say, to the right, there's a small probability that it won't quite happen. So I'll have to read my notes again you'll have to read the book to see what the actual setup is actually. But I think that the probability is not totally exact, in the sense that if you say I want to go to the right, it's very, very likely to happen, but there's a small probability that you could go to some other neighbouring square. So it's unlikely, but it could happen. So somehow maybe the controls of the plane are not quite as responsive as you thought they would be. So what that encourages you to do is to take the path which is, in some sense, the most robust one, subject to possible. So this corridor here would be quite dangerous to go down, because there's a small probability that you would hit this village or this sort of off the runway part. I think that's what's going on.
Just a quick question. Why did disaster zones change colour? I didn't.
Well,
you can never go on them, right? So why would?
Well, they don't. This is the way MATLAB's plotting and stuff. I think that it's the utility of being here is still very, very bad, but the utility of being here now is very high. It's just when MATLAB plots this thing, what was originally value of 1 or whatever, it stayed value 1, but this is now got a much, much higher value. So when MATLAB plots this stuff, but the question is why is this one different from MATLAB? Yeah.
Well, like we said, like around the landing strip, there's like the disaster areas where you can't go.
Yeah,
so
that's
why
true.
should you do that?
That happens because
Can you fly over them, but you can't land
well,
them?
it's bad, but it's not infinitely bad. So if you were to go here, I mean, this doesn't really make sense in terms of planes flying, I confess, but there is a possibility that you could, somehow sort of, barge your way through this, sort of poor barrier and get through then to a good position later. But it just costs you an awful lot to do that.
Presumably that's why just around the final spot, they're very green. Because if you'd started just outside the final spot,
right.
It might be the cheapest thing just to fly straight onto there and sod it, rather than paying the other costs of going all the way around.
So there are, it's perhaps not the world's most sort of realistic example, but you get the idea. It's kind of interesting. I think when I'll run the demo again, and you notice how in the value iteration things sort of tend to propagate back from high value positions. This is the value surface again, and we've just plotted in a different way. So these are, you don't see it very well, of course, but there are something of very, very deep holes here where you don't want to be. These correspond to the villages. This is kind of this is the optimal thing. We want to sort of, come down here, keep going uphill, avoiding these big holes, and sort of keep going up this slope to get to.
So you're saying the decision process you take once you're travelling is to always go to the neighbouring one that's got the highest probability. Is that actually a globally but that gives you a globally optimum solution, even though it's local decision?
That's right, yeah. So you go to, what you'll do is you'll take the, if you're in state S, you look at the neighbouring states that you can go to, S primed. Each of these S primes has a corresponding value. But there's a probability that you, let's say S prime given state S, so the value, you want to take the sum of S primed, you want to do the max, find the argmax of D. So in other words, you're some for state S, you want to take that decision which gives you the highest expected value. And because this transition matrix in our case says you can only go to states which are neighbouring the graph and correspond to, if this were deterministic, it says that if you want to go left, you can go left, and you will end up in the left state for sure. This would just say go to that value which has got that neighbour with the highest value. But if this is not deterministic, it would say go to the neighbour with the highest expected value. Given that, for example, if you say go left, there's a small probability that actually you might not actually go left, but you may end up in some very disadvantageous state. Okay, but but you're right. I mean, that's the interesting thing about what's happened here is that the optimum decision, the optimum global decision, or the optimum global path is given by the sequence of optimal local decisions, and that's the kind of the big win, if you like. So I just run it again, just to go delight. So I think this is value iteration. No, it's policy iteration. Sorry, going on here. Policy. Yeah, really good. So one of the exercises or the assignments, I think, will be to extend this case, and you have to solve it where I think you have a drunk pilot or something like that. It's kind of like things are not working so well, and you have to figure out what the optimal thing to do is in that situation. Okay, so I don't have any slides for this, but I just wanted to give you an idea that there are many scenarios in life where you could imagine applying such a similar kind of market decision process, an MDP. And one of them is in finance. So you might think about trying to, where should you put your money? So you could say, I want to retire, say, in 50 years' time. Well, not me, so yoga students. And you might say, well, okay, I would like to have a certain amount of money at the end time. You might say, I would like to have £1 million in my pension fund, basically like that, at that retirement age. So one thing you could do is you could say, well, I could put all my money in the bank, which is fine, but that has a very low interest. So you would say, this is time, T, and maybe there's some end point here when you're going to retire. And if you put all your money in the bank, your money, let's say interest rates are pretty stable, they're not really going to fluctuate much. And so you're going to accumulate wealth in your bank account, and you get to some kind of retirement pension fund. The other thing you could do is you could put your money in the stock market, and that's so generally much more volatile, right? So you could say, if I put my money in all of my money in the stock market, it might do really well, but it might go really badly. It's kind of much more variable. If you're unlucky, you lose. if you're really lucky, more lucky, you win, right? But so it seems kind of clear. But let's imagine that you say, I'm a little bit greedy in the sense that I really want to outperform the bank. Right? I want to retire, and I want to be able to, have that boat. And that boat is going to cost me this amount of money. So there's no way you can get that boat by putting your cash, all of it, in savings, all in the bank. It's not going to happen. With probability 1, it will not happen. So you need to take some risks. You need to put money in the stock market. And then the question is, what fraction of your wealth should you place in the bank versus what fraction of your wealth or your savings you put in the stock market? And this will be a dynamic process which will change. So at times that, one, we will make a decision about what fraction of our wealth to put in these things, and we will change it through time. Now we can model the situation which with an MDP, with a Markov decision process. So we could say, well, we can have a Markov decision process which says how the interest rate for the bank changes is some kind of Markovian process. So the interest rates only change a little bit based upon the previous interest rates. It might go up by 1% or down by 1%, something like that. Similarly, we could have a Markov process for the stock price that could go up, by some amount and down by some amount, but maybe it's more. Maybe it can go up by 10% and down by 10%, something like that, in one time step. And then, depending on what happens, whether or not so the decision will be, in this case, what fraction of your money to place in the bank or in the stock market. And you might have, say, for example, a discrete set of values. I might put, say, 0 in the stock market. I might put, 25% in the stock market, 50% in the stock market, 75% in the stock market, or 100% in the stock market. So there might be some, say, discrete settings of your cash that you want to place in the stock market. And so that will be your decision variable d at time t. So it has, say, 4 or 5 states in it. And then depending on what decision you have there, and actually what happens with interest rates, that will determine your wealth. Right? So what you will see is your wealth then, your savings are going to start, hopefully going up, then they go down. And then what you'll do is, maybe you will take decisions at some. You might say, I'm now here, based upon my current understanding of the stock market. Am I likely to get to this future desired retirement wealth? Taking into account not just the fact that the stock market's varying in the future and you don't know how it's varying, but that you will be taking decisions in the future subject to those conditions. Right? So this is the kind of the global situation like we had before, that you're going to take a decision here such that which will be optimal in the sense that the future decisions which you will take in response to what would happen in the future will be still optimal, and in the sense that you will have a high expectation of reaching your desired goal. So it's a non-myopic process. It's not that we just sort of see where we are now and say, well, okay, I simulate all trajectories, not taking any other decision in the future, but just what would happen with interest rates from the current point. I take that single decision now, which would give me the most likely expected future wealth. I'm going to take that decision, which, bearing in mind that I will react to what happens in the future to give me the optimal future return. Okay.
Do you want to run a Monte Carlo simulation on that as well?
No. It's not a Monte Carlo simulation. But this is a point which I never seem to be able to get across very well to people who usually work in finance, which is a little bit disconcerting, but anyway. But this is the way to do it. So this is how you would solve your, obviously it depends upon the model, It's all conditional upon the fact that your interest rate model and your stock market model are reasonable. But given that you've got reasonable things, then this is the optimal thing to do. So the details are described in the book, but including the demo. But we can try to see, if we're lucky, a little laptop may be able to deal with this. So this is time here. So in this case there are 40 years. So at some time point, 40 years in the future, you want to retire, and then this is the, oh gosh. So the dotted one was the bank interest rates, which were kind of slowly going up. The more volatile one was the stock market interest rates. So I just sampled, something that actually, this is what's going to happen in some particular environment. Okay, so in this particular situation, that's actually what happened. So you came along. So you don't. Okay. So you have a model for the situation, and the first time point, you don't know what happened, and you take a decision, solving this market decision process about what fraction of money to put in the bank and what fraction to put in stock. And you decide to put whatever it was. Half of your money in the bank in this case, and half in the stock market. Okay. Then some variable was revealed, namely, actually, what is the interest rate at time step 2, and what is the stock market doing at time step 2? And then to restart this process, to say, okay, that's actually what happened. What now should I do? What decision should I take? And you resolve the Markov decision process, given that you are now at this initial starting point again. Okay, so that's why that particular trajectory was actually what happened for this particular customer. This is actually the scenario of the actual interest rates and the actual stock market for that particular customer. That's the particular future that happened to him. So that will be revealed as we go along, and we need to sort of see what happened for this particular person. And as you can see, we are changing the fraction of money that we're putting in. So at some points, this is our desired target, and we make it. And once we've made it, we just put all of our money in the bank. There's no point risking it anymore because we've reached our desired investment goal. So you'll see that at some points, if you run these simulations, you see how well you're doing, and you'll find out that as long what will happen is that as long as you get to a point where as soon as you get to a point where you can be confident that just by putting your money in the bank you will reach your expected target, you stop taking any risks. So in the beginning you have to take a risk because there's no way to reach this goal. But at that point, if you're lucky, the stock market performs reasonably well, you stop taking any risks anymore because you don't want to risk not having the boat. So that's what's going on here. So you start out putting half your money in the bank, then even more, and then you're reasonably confident here that things are going to go well, but you need a little bit of help in the stock market. But then at the point, after 20 years, the stock market performs so well in this case that you just put all of your money in the bank. Okay. Doesn't always happen, of course. But so that's putting all the money in the bank would have given you a value of this is the kind of thing that one ought to be doing with banks. I guess they do this as well. But it's not. The point here is it's not myopic. These decisions are globally optimal for the future, taking into consideration that you will be able to respond in the future to the changes in the scenario. It's not just where I am now, what decision should I take, simulating into the future what the stock market would do, because that would not take into account the fact that you can change your decision in the future. Otherwise the myopic thing is suboptimal. It's a bit complicated concept, but it's true. Okay. All right. So that's Markov decision processes. So just that's looking back. This is again a form of inference, right? So now all we've done really is we've coupled together belief networks with the idea that we can have some associated utilities hanging off various variables in this belief network, and that we can call an inference diagram. And there are some structured inference diagrams, for example, the Markov decision process, for which there are very convenient algorithms there. So that kind of Bellman equation, recursion, would actually essentially be what would happen with the junction tree algorithm when it would apply to the inference diagram in that case. Because the junction tree, which would correspond to the inference diagram, the NDP, is itself very simply structured. Right? So it's kind of easy to do. Now, an interesting question is, what would happen if you didn't know some of these transition probabilities? Right. So this is the scenario of reinforcement learning, and this is sort of a little bit starting our discussions about learning, which we'll be focusing on for the whole rest of the course. So you could say, well, let's imagine I'm an organism, and I want to survive, right? So I have a kind of utility, like whether I'm alive or I'm dead. If I'm alive, I have a high utility. If I'm dead, I have zero utility. And there are many things that I may need to do along the way, but I might see this sort of tempting-looking plant, and I'm starving, so I should eat it. But then you realize actually later on, well, this is a bad thing to do because this plant made you a little bit ill, which maybe didn't kill you immediately, but it sort of impeded your ability to find other food in the future. It kind of limited you in some sense. So you would then need to understand a little bit about what happens if I what is my environment like? What happens if I take a decision? How would the environment respond? So you may see things which kind of well, maybe a better scenario would be like a maze scenario. So let's say that you're in a maze and you're just somewhere in this maze and you don't know what sort of doors are possible. So you may say, well, maybe there's some kind of transition structure. So you may say, well, I start at some point in this maze and I realize that there's a door here which enables me to go from this state to this state. And maybe your aim is to get out of this is the exit of the maze, so you need to get to this state. And so you're just thrown in, somebody says, they just throw you blindly into this maze, and you don't have a map of the maze. And the question is, what to do? Well, if I knew what the map of the maze were, I could figure out what the optimal thing to do. I just solved the Bellman's equations and I'm done, right? I know how to act optimally to get out of the maze. But if I don't know this, I have to learn it by interacting with the environment. So I try in this maze, maybe corresponds to a set of doors or corridors that I could go down. And I realize I can go down or through this door to some new room in this maze. So this transition is possible from state to state. But then, I think, okay, I tried something else. So maybe in the beginning, I have a very poor understanding of this thing, and I just randomly go around and I find out that I cannot go this way. So maybe that transition that you learn is not possible. But then if you're lucky, maybe you you went through a sequence of possibilities here, which got you to the exit. Now maybe your reward or your utility, also you have a high utility of going to the exit, but maybe there are other sort of nice things along the way. Yeah, so maybe there are rewards. There's a pot of gold, also maybe in this maze. So you didn't know it, you didn't know where it was, but now let's imagine that you then you build up some knowledge about this transition structure by just randomly exploring around, and then somebody places you again in the maze at the same point, and they say, okay, what are you going to do to get to the exit ultimately? You say, well, I don't know about the rest, but I know there's a path here which will get me there. So you're just now going to go along this possible path because you have no idea about anything else. But it could be that actually there's a pot of gold here in this state. And actually the best thing to do would be to say, well, to take some apparently suboptimal exploration step and say, well, maybe I should then start looking around here. These seem to make me go away from the goal, from my current understanding of the maze, my transition probability. And maybe I need to explore. And if you're lucky, you'll explore, and you'll find, oh, actually there's a pot of gold in this state here. So when you're placed then in this state again, there's no way you do that. You go to the pot of gold and go out. Okay, so this is the exploration-exploitation dilemma, in the sense that in reinforcement learning, we are done. If we know what this transition probability is, it's not reinforcement learning anymore, it's just solving a Markov decision process. And reinforcement learning is Markov decision processes without knowing, though, what this transition probability is. And you need to learn it based upon interaction with your environment. But you can see fundamentally there's going to be a trade-off there, in the sense that if we learn something about this transition probability, we may think we are doing well, and we know how to then act optimally because we just solved the Bellman equations and we seem to be done. But it's clear that there are scenarios where actually that was poor. You should really have sniffed around. Maybe there are pots of gold elsewhere. In survival, maybe there are better things to do. There are partners which are better than the one you have now, or whatever the setup would be. Maybe you need to explore before you act, and this is a trade-off which is very difficult to somehow quantify. So it's a little bit in reinforcement learning. There are some mathematical ways of phrasing these kinds of scenarios, but they are, in general, there's no kind of optimum way to split as to how much you should explore versus how much you should just exploit your current knowledge. And there will necessarily, in some sense, generically be a heuristic as about how greedy you should be in exploiting versus how curious you should be in exploring. There's no kind of easy way to characterize that. Okay, so but that's reinforcement learning, which you can learn more about in the advanced topics class. But I mean, I think I personally like to view, this is my viewpoint of reinforcement learning. It's just MDPs, but you don't know the transition matrix, and you have to learn it as you're going on. Okay, so that's what I'm trying to say here. Yeah, so this is just to finish off this topic. So there are we can use influence diagrams. We can solve them using a junction tree. If we did that for the MDP, it would be an easy junction tree, corresponding algorithm. And there are many problems actually in real life which are Markov decision processes. Investments, scheduling various things like how do you figure out where to send planes, optimize how do you, if you've got a complicated airspace and you need to kinds of competing objectives, like planes shouldn't get too close to each other, they shouldn't take too long to fly. Each plane's also got its own kind of fuel issues. Maybe this plane has to pay a certain amount of money in a fine if it doesn't land in time. And how, based on all of these things, how do you decide which plane goes where as a controller? And this essentially an enormous markup decision process problem. And at the moment, it's just done by some guys looking at screen and trying to figure it out. It's horrible, but actually they really want to optimize it. They want to make computer things which actually do this optimally to some extent. I mean, it's a very, very difficult problem. But this is a dream of the European Union to have such a system, rather than a bunch of guys trying to figure it out on the fly. So another situation is in a case where some of these variables are not going to be observed. So, for example, in the markup decision case, you might have some subset of these variables which will actually never be revealed to you. And this complicates the process, because when you think about this, you have to sum over those variables first, because they will never be revealed. And when you do that summation first, it couples all the other variables in the graph together, and the markup structure vanishes. So we can no longer efficiently distribute this sequence of sums and maxes over the rest of the graph, because the structure has disappeared. So these are called partially observable markup decision processes, POMDPs, and these are very important. There's a huge number of important problems which are POMDPs, but unfortunately there is no known efficient algorithm for solving POMDPs, and it's a very active area of research for the last 30 odd years, and it's still very, very challenging and difficult to do. And game theory is also kind of related to this as well, but there, it's more adversarial, but it is frameable as a kind of MDP as well. Another thing to say though is that in reality, you can think about game playing or those kinds of things can also be seen a little bit as MDPs, but the tricky thing there is the number of states of these things is huge. So that's another major challenge, that you could have an enormous exponentially large number of states of games or planes in airspaces and things to do this. So it's a kind of a little bit of a trivial statement to say, well, it's an MDP, yeah, but it's an MDP with 15 trillion states, so that can't be solved. So how do you get around that? That's another major area of research. Okay, this concludes decision theory. Okay, so that's good. Any questions on decision theory before we move on? Okay. So unfortunately, I didn't show the notes to you. In the last half an hour, we finished slightly sooner than I was anticipating. So we're going to move on to the next topic. So we don't have this notes. All right. So we're done with inference now. You know how to do everything. Singly connected graphs, multiplicative graphs. You even know how to do for decision problems. So it's great. You've got actually an incredible tool set now. You may not know it, but you have. Now, though, we need to link all of this with data. So we're going to get to the problem now, the issue now of how to learn these probability distributions with data. In the past, we've seen it. So let's start right from the basics. We're going to have some coins, and we're going to toss coins, and we're going to try to figure out what's the probability of a coin becoming a heads. So Vn will be 1 if on the nth coin toss, the coin is heads, and Vn will be 0 if on the nth coin toss, it comes up heads. So you're going to get a sequence or a set of these leaves, 1s and 0s. And what you want to figure out is, what is the probability of the coin going to come up heads? So the way to model this is to say, well, look, this theta is going to be that probability of a coin coming up heads. So in other words, given theta, probability that on the nth toss the coin will come up heads is theta. So given theta, probability that it comes up heads is theta. Right? So the variables in this situation, in our probabilistic modeling thing, are we've got n variables, and because there are n coin tosses, they're all ones and zeros, and we've got this theta, which is the probability there. So we need to make a joint distribution over all these variables, v1 through theta, n through theta. So that's our usual, sort of modeling setup. So what we're going to do is going to assume that this thing here, v1 through to vn, and theta can be written as p of theta, p of v1 through to n, given theta. That's always true. That's just base rule. Now we're going to make an independence assumption, namely that if you tell me what the probability is of this coin coming up heads, that's all I need to know, in the sense that these are their independents. Each of these individual coin tosses is independent. They're all independent of each other. So the only thing that's sort of physically influencing these, there's nothing which is coupling or physically influencing the heads or the tails, except for the fundamental probability of the coin coming up heads and tails. There's no coupling, so in the sense that, if it came up heads before, it's not going to influence whether or not it comes up heads in the future. But the value of v, if I know what the underlying fundamental probability is of a coin coming up heads. Do you know what I mean? Just for those, so in other words, v1 given v1 given v2 and theta equals p of v1. v1 does not influence, the actual value does not influence what happens for v2. So this is our belief network. And now we're going to observe these things, ones and zeros, and then we can come up with a posterior probability of theta given these v's. Okay, so if I start out with, say, this is some probability, prior probabilities to my belief as to what the bias of this coin is, what is the probability of coming to heads. This is going to be conditioned upon, and I'll end up with the posterior distribution upon this thing. So we can replace this sort of replicated structure here with the n trials of flipping this coin with what's called a plate notation here. So what this plate does is just take the object inside the plate and replicate it this number of times. So this is a shortcut notation for that. It's the plate replication notation. So let's start out with a simple discrete situation, so we don't get into continuous variables too much. Let's say my prior belief is that there are only three kinds of coins. There are coins which come up heads, with probability 0.1. There's a kind of coin which comes up heads with probability 0.5. And there's a kind of coin which comes up heads with probability 0.8. So this one here would correspond to an unbiased coin. And these two here are biased coins. And my understanding of the world is expressed in this way. You may say, oh, that's stupid, that's wrong. But that's fine. You can argue with that. But this is my subjective, personal beliefs about the world of coins. So I can write that down. 0.1, 0.5, 0.8. These are the corresponding prior probabilities. Okay. Then the posterior is theta is given by this expression here, which is proportional to p of theta times by these individual probabilities. Okay. Now, this probability here can be re-expressed in this way. So, So let's say that you observe v1 is 1 and v2 is 1, V3 is 0. So head, head, tail. Okay. So we need to figure out what's the probability of V1 equals 1 given theta multiplied by P of V. This is for this term here. Okay. P of theta, P of V2 equals 1 given theta, P of V3 equals 0 given theta. So this one is equal to theta. This one is equal to theta. And this one is equal to 1 minus theta. Because it's 0. Okay. So in other words, this is equal to theta to the times, if it's true that V1 was 1. And I would get, in general, I get theta for a variable which is in state 1, and I get 1 minus theta for an observed variable which is in state 0. So V, any V, can only be 1 or 0. So only one of these two terms is ever going to. So this notation means that this object is 1 if the thing inside is a true statement. Otherwise, it's 0. This is the indicator function. Okay. So we're going to have a product of these guys. So we can just write it like that. So then when we take this product over n, this becomes equivalent to a sum over I over n. So over n. Okay. Clearly here, you can see right here, you get theta squared times by 1 minus theta. Theta to the number of times it was 1 times by 1 minus theta times it's 2. Okay, so this is the posterior is our prior, theta to the power number times its heads, 1 minus theta to the power number times its tails. And yeah, it's the corresponding counts. So let's say that we observe 2 heads and 8 tails in 10 tosses. So we started out with the prior here. So a priori we were fairly confident that most coins are fair. But after seeing this evidence, these coin tosses, we have this posterior probability which says, well actually we're less confident now this is a fair coin. It's, maybe it's quite plausible that it's we've got a biased coin here in our hands. It's one of those funny ones, which come up tails with a high probability. So that's the updating effect from the prior to the posterior. Now, one question for you guys is how do I know what the normalization term is here? So I said it's proportional to this thing. But here I wrote down actual, well, I didn't write the numbers down here, but I could write down actual values for this, this, and this. Numerical values. I didn't write a scale here. How do I know what that scale is? How do I figure out what is the actual, so you know what this value is, the prior. You know what this, so for each of the 3 values, you've got 0.1, 0.5, 0.8 theta. And you can work out these corresponding quantities, right? But I'm saying that posterior is only proportional to this thing. So how did I figure out what the normalization, what the actual probability is ultimately? There seems to be a missing normalization constant, right? So how did I get that?
You integrate over theta.
Yeah, exactly. So whatever it is, I say I've got this p of theta given the data, right? This piece is proportional to some function of theta, a complicated expression. Well, this is exactly the same thing as we had before. So this means that actually it's equal to constant times by theta. And in this case, we've got discrete variables actually. So it means the sum of the states of theta, of p of theta given the data, which is equal to k times by the sum of the theta and theta. It must be equal to 1, so k is equal to 1 over some states of theta. So what this means is that I simply, for 0.1, I work out this thing, and I get some value, some small value would be 1 to 0.1, 1.5, and 0.8. I'll get some number here, 0.001. I do for 0.5, I get some other number, 0.032, 0.8, whatever it is. I get 3 numbers. I then simply replace this number by that number divided by the sum of those 3 numbers. That's what it's the same. And that's how I recover the unknown normalization term. And it's easy to do because I've only got 3 states to worry about. Okay, so one important point here is that it's not that we've got an absolute hold on what is the value, what is this coin that we are faced with here. All we can say is that I have some, I'm pretty sure it's not a coin which is biased towards 0.8, but I've still got a distribution which has got appreciable mass in more than one state. And there's nothing, really here which says, how should I summarize this distribution? It's up to you if you decide, well, if you want to take the a posteriori most likely state, namely 0.5, then that's up to you. But I'm not saying that you have to do that. I say nothing, probability at this level is not saying that you have to summarize this distribution. All we're going to be discussing is how to get this distribution. What you decide to do with it after that is up to you. There'll be additional utilities that you can apply to decide how to summarize this distribution if you wish to do that. So let's continue this process now. So before we had 2 heads and 8 tails. Now we're just going to multiply that by a factor of 10. We have 20 tails and 80 heads. Okay, so the fraction is the same as before. And we work out the posterior, okay? And we get this situation now. So what's happened here is that actually we're pretty confident of the 3 possibilities that we had available. It's got to be really this one. It's biased towards tails. So this is kind of interesting in a sense because in both of these 2 situations we had 4 times more tails than we had heads in the observations. But it's the actual number of them, it's not just the ratio of them which is important. The fact that we had many more observations here has totally transformed this posterior distribution. We're absolutely confident now, where before we were only slightly confident. Okay. So it's not that when you do inference of these parameters, which is what learning is about, it's not just like, well, if somebody said, I had 4 times more examples at one state than the other state, that's sufficient information. Actually, you really need to know the number of it. It's not just the relative number, the absolute number that counts. In this case, you're super confident. And why is that? Well, intuitively, of course, this case here, it could just have happened by chance. Even for a fair coin, it's not improbable that you could have got 2 tails coming up out of 10 tosses. It happens. Right? It's quite plausible. On the other hand, if you said I tossed a coin 100 times, and 80 times it came up tails. Is that likely for an unbiased coin? It's very, very, very unlikely. Yeah. So that's what's going on here. All right, so you might say that's fine. So I have to apologize because now we're going to for the first time talk about non-discrete variables. Okay, we're going to talk about continuous variables. So you might say, this idea of a discrete bias of a coin is very unnatural to me. I don't like it. I want to deal with I want to use continuous variables. What could you do? So this is just a sort of flavor for how you might approach the same question from a continuous variable viewpoint. We're going to have a prior, as before, p of theta. Now theta is a probability of it coming up heads. So that theta has to be a value between 0 and 1. It's some number between 0 and 1. But now we're going to assume it's continuous. Any value between 0 and 1. So we need some probability distribution such that when we integrate over theta, it's going to integrate to 1 over the range of possible thetas, which is between 0 and 1. So we might say, let's use say a flat prior for theta. Let's say we have this theta between 0 and 1. And we want some p of theta which is constant, which is flat. So the flat prior in this case would be that it would have value 1. So because now this is, I say probability is a probability density function. So you might say, how can the probability be 1? It's a probability density continuous variables. In the sense that this thing, if I integrate from 0 to 1, p of theta d theta, well, p of theta is 1, right? So it's the integral of 1 d theta between 0 and 1, which is 1. So it's kind of weird. So probability density values can be between 0 and infinity. They don't have to be between 0 and 1. So in this case here, we can now do the same thing as before. So our posterior, given the set of visible variables that we have, the set of observations, v, the coin tossers, is proportional to theta to the power n minus h, 1 minus theta to the mt. The prior probability was 1, and we've got some constants. And this constant is again, in this case, given by the integral rather than the sum. So that you have to integrate this thing to renormalize it. So c is given by this integral here, and this is the beta function. This is the definition of the beta function. So this objects mathematically, if you have something integral between 0 and 1 of x to some power, 1 minus x to some other power, that's defined to be the beta function. Okay, that's just written like this. They offset the power by 1, so this is the beta function of the first argument plus 1, and the second argument plus 1. And then you just go and look that up in some table, or MATLAB will compute it for you. There's no closed form expression for this beta function. It's computed in some sort of numerical way. Okay. And then you can plot for the case of the 2 heads and 8 tails. The posterior probability is then given by this. This is the posterior probability density of theta. Okay, so the most likely value is 0.2, but you've got appreciable mass in many other states around there as well, many other values for theta. The case when we've got more, we have 20 and 80, the posterior starts to peak around this 0.2 more. So we get this kind of sort of, what's the word I'm looking for? Coalescing, or concentration, that's the word I'm looking for. Effect. Okay, so things start to peak around the most likely value. So this peaking, why is that happening? Why is the peaking going on there? Well, let's go back to this thing here. under this IID, this independent identically distributed observation assumption, it had this product given theta of the observations, right? So just think about what that's going to do. It means that every observation is going to impact on this posterior by a factor, right? So you get these exponential sort of factors coming in, because when you've got n observations, you have a product of these numbers. So what that means is that is going to shrink this posterior around that theta which has got the highest value. And that's exactly what the central limit theorem is doing. So you've all done this, right? You've all done the central limit theorem at some points in your undergraduate careers, right? And well, that's exactly what's going on here. We can do the same thing. We can write this down. I mean, another way to write this down would be product over n of P of V n given theta. You can write that as e to the sum of the log, e to the sum of n of the log of these probabilities n given theta. And what you do in the central limit theorem then is you simply expand this around the most likely value. And this thing here is going to scale typically with order n. N is the number, so it's going to put a sum over n here. So you get, roughly speaking, it's going to go e to the n log theta. Where this is kind of, theta is close to the optimal value. So that's why you get this exponential concentration in the posterior distribution around the most likely point. And that's the heart of the central limit theorem. So that's a numerical demonstration of this concentration effect. How are you doing? You want to keep going? Is it enough? It's enough for today, isn't it? Is it enough for today? So let's stop there. Is there anything you want to ask me about? So look at I will send out the questions. I'm hoping tomorrow. Okay, for the next assignment. It'll be a tough one, let's say. So do ask Chris on Friday. Make sure you try to get a copy of the solutions for the first half of the exercises. Don't forget to ask Chris if you've got any other things that you're not clear about. Otherwise, I will see you guys in 2 weeks' time. And do email me if you've got any questions in the intermediate period. Okay, have a nice reading week.
Especially